Distinguished participants, ladies and gentlemen, I would like to give you an agenda for today's conference. First agenda would be a plenary session presenting prominent experts from Indonesia and other countries. This session will be chaired by Dr. Erwin Makmur. Dr. Erwin Makmur is the coordinator of Meteorology Division, Center for Research and Development of BMKG. After the plenary session, there will be a parallel session in 5 rooms representing the topics of this conference. So without further ado, I'd like to pass the microphone to Dr. Erwin to chair the plenary session. To Dr. Erwin, the floor is yours.
Okay, thank you, Ms. Sheila. So, hello everyone. Good morning from our colleagues from Europe and UK, and also good afternoon, our friend from Indonesian scientists and also from Southeast Asia countries. So, welcome to the second day of the second international conference on tropical meteorology and atmospheric science, ICTMAS 2021. So, first, let me introduce myself. I'm Erwin. As Ms. Sela mentioned, that I am a coordinator of the research of meteorology from BMKG, and also I'll be responsible for hosting this presentation today. And I'm glad to welcome for all speakers and participants. In today, in plenary session, so actually we have 8 outstanding speakers who does come from multi countries and then institution. But at last minute, one of our presenter canceled his participation due to the other activity. And then for this session, so we will have 15 minutes for all speakers, including the presentation and then question and answer. So I hope all the floor, you have some question, please write down in the chat room. And then we don't have some oral question and answer for this session. So as you know that in this session we have 7 speakers. So after the first speaker, so we have 5 minutes for break, and then after that we continue with the speakers, and then also we conclude with the question and answer. So for the first speakers, we have Dr. Yus Budiono. He is a researcher from BPPT, and then Dr. Yus Budiono is a research associate for the Agency for Assessment and Application of the Technology BPPT in Jakarta since 1995. In the office, he has led various research projects such as liquid and solid waste management from ship and harbor in Indonesia. So his expertise is for the dynamic model, flood risk analysis, decision support system, and else. So, Dr. Yus, your time is 15 minutes. So, 3 minutes before the time, so I will remind you for this session. So, Dr. Yus, time is yours. Thank you. You still mute your microphone, please turn on. Okay, thank you.
Thank you. Thank you for the chance, and see you everyone here in the room. I'll proceed to my presentation. I'll share my screen. I hope now you see. I hope now you see my presentation in the screen. I will discuss the early warning system from the above, from the theory down of that to reality. I myself am Yus Budiono from Agency for the Assessment and Application of Technology in Malaysia. Yes. In this event, the early warning systems, I will discuss three things. First, the flood early warning system, and then the landslide early warning system. Uh, Both are related to atmospheric disaster, and then the third one, the tsunami early warning system. I'll discuss more on the benefit and cost analysis based on our 2017 calculation. This work has been published, and then my research with my ongoing research, which is progressing, uh, started in 2019 and then in 2020. The screen tells us how I calculate the benefit of flood early warning system. So first, beforehand, we already developed damage scanner. That takes three major elements, which are the hazard, exposure, and vulnerability. And the flood early warning systems uh, change this part, the vulnerability, and we solve the early warning system benefit by using survey. And when we input the normal element, we got the flood risk without flood early warning system. And then when we did the survey, the vulnerability change, and then we got new flood risk with flood early warning system. This is the basis of vulnerability that by. So the red full line here is the basis of our calculation without flood early warning system, and then the dotted line here is the realistic scenario which came out from the survey, and then the dashed line here are the optimistic scenario. Note that everyone respond to the early warning system. So this is the result of our calculation on the realistic scenario, which we survey. 1.9% of total risk of Jakarta flood risk is saved by early warning system. And if we limit the calculation on the residential land use class, the effectiveness is 13%. Because within Jakarta, there are, and three of them are the residential land use classes. And the optimistic scenario, there are 12% of flood risk reduced. Note that everyone will respond to flood early warning system. And if we limit on the residential land use classes, the save will be 84%. I'd like to restate again that this flood early warning system only apply to residential land use classes, while other land use classes, which are industry, commercials, office, and others, they don't have quiet respond to flood early warning system. I give you the illustration, for example, that machinery in the industry can be moved to other place when flood arrives or about to arrive. And we were curious if this will be related to the source of disaster, but apparently, when we plot the damage for one, and then we draw a dash line there, the fit was not very good. So we suppose that flood source or the disaster source is not very much affect the effectiveness of flood early warning system. And secondly, we also in 2019 started the rainfall-induced landslide. We have some instruments for early warning system, monitoring system, and this we develop the threshold. we we include many things in the element of model, including rainfall pattern and intensity, and we also suppose that the rainfall will do something with the vegetation, has some relation, and we also consider soil changes, soil type in the field, and then the morphology and slope, and whether there are some work on the land, on the soil. As a result, we observed that there are four major elements to affect early warning systems or landslide, rainfall induced landslide threshold, which are the precipitation pattern and the 3 days cumulative. There are quiet discussion on this, which takes more than 1 minute or 5 minutes. So I will not discuss here. And the second important thing is the terrain steepness. In the field, we found that the steepness is 45 degree and more. The soil type is quite homogeneous, and land cover dynamics are also homogeneous. But we found in the reference that this affect much on the rainfall induced landslide. Um, Unfortunately, these two are constants for us because in our field we take the Western Java, which the behavior of the land cover is similar, uh, and then the soil type are also similar. So we haven't gone to early warning system at this part. There are still many uncertainties to solve. And then this is our latest research, which for me is quite interesting. We developed tsunami early warning system, several types of them. The buoy system, the tomography that check the ground, and then advanced CBP that checks the behavior of the water. But my role was to see whether the tsunami early warnings, what is the benefit of the tsunami early warning system compared to the cost. I haven't gone to the cost, but we did the observation in Simalu, because Simalu Island, people recognize the smong, the local knowledge. And then we also did research in Banten, and Aceh mainland actually also recognize local knowledge related to the warning system, which namely IBNA. But we didn't went there to observe this. Uh, uh, Benefit and cost analysis methods. We did random sampling. We interview 50 more family leaders, which in 2004 already had a family, and we found that 30% of them were female, at least in our sample. This is the likely benefit of early warning system. When we design our research, we were quite pessimistic that there will be benefit. But apparently, because we see here, and there are many figures of this, that when tsunami strikes, everything is vanished, everything is gone, nothing can be saved. But in the end, this is still qualitative. Our enumeration showed that people who evacuate, they take also the logistics. People recognize bring one bamboo of rice, which is 15 kilograms. And then that the females take also the jewelry, which are with them in the culture, and there are also pet kettles. Didn't calculate that. We didn't consider this because apparently the escape is not interfered by human. Yes. and subsequently from the not result from the early warning system, because this cattle are raised in the wild. But what we assured is that tsunami early warning system require good understanding of the phenomenon. So and similarly, disseminate the knowledge to the grandchild. So tsunami occurs there in a period of 100 years. So information from the father were not important. The important was from grandfather to the grandchild. And we also found, surprisingly, when we visited Banten, do the same method there, found that there already local knowledge, namely Laut. But we still investigate this. I mean, the survey is still going. It doesn't produce anything yet. And also we found in the reference that Aceh actually recognized IBERNA. There is a kind of early warning system, social early warning system, which were gone reportedly because of the long fight in Aceh. And last word, we know that in our consideration, we only calculate the tangible asset, tangible that we can quantify, but apparently there are also intangible. So even though second, even though capital investment to early warning system is significant for flood, because we can calculate the effectiveness and the operational is very cheap. But somehow the tsunami early warning system would also important, even though the benefit cost analysis is very low, much 1.0, which that means its benefit and cost point of view is not feasible, but somehow it could save lives, like in Simalu and in Banten, Kabupaten Pandeglang, near the national park. And also, we need to consider that early warning system is not just the hard measures, the instruments that we build, but also soft measures, which are the model that work in parallel with
You still have 2 minutes.
instrumentation, but also the social and yes, I'm about finishing my presentation. Thank you. And other thing which is important is how to disseminate this technology and the soft technology to people on how to respond or whether to adapt or for the government to mitigate. This is the figure that will remind us the importance, the failure actually of the hard structures and the benefits of local knowledge. That's all of my presentation. Thank you. I'll return the time to moderator. Thank you.
Okay, thank you, Dr. Yus. So it's very interesting information for us. We're still waiting for the question from the floor. As you know that there's one question for you that from Mr. Dian. Sorry, I think it's Miss Dian.
Yes.
The flood early warning system are implemented in many parts of the world, but early warning do not always translate into an emergency response from all individual at risk. Do you think it is important to examine challenges such as warning, communication, and community response capabilities? So, do you have some comment for this question?
Yes, thank you for the question. That is the challenge to all of us to BMKG, for example, because BMKG broadcast the warning system, that we need to observe what is the best practice, or what is the crucial part that we need to disseminate to people. I mentioned in before in the last word that social intervention is quite important. And MKG, I think there are 300 branches all over Indonesia. So I think we need to plan how the early warning system need to be disseminated to people. I think that will my answer to Ms. Liang. Thank you.
Okay, thank you, Dr. Yus. So, thank you again for Dr. Yus. So we will move to the next speakers.
Thank you.
Our next speaker is Dr. Rahmat Hidayat. Dr. Rahmat Hidayat is a lecturer from the Department of Geophysical and Meteorology, IPB University. So now Dr. Rahmat is the head of the Department of IPB University. So he has some experience for the interaction with ocean and land for the and also for meteorology. So Dr. Rahmat, your time is 15 minutes, including question and answer. So now time is yours.
Okay, thank you, Chairman. Good afternoon, everyone. And from college, from Europe, good evening, and even for good morning from our college from Europe, and also almost evening, maybe in Japan time. So today, I would like to present my research and collaboration with our team. Could you see my presentation? Okay. Today's presentation, the variability of the South Pacific Convergence Zone and the implication for Indonesian rainfall. So this research is conducted by team, me and also our student, postgraduate student, Putu Ninin. And then here, the background of this, sorry, could you hear my voice clearly? Because
yes, very good.
Okay, I will continue. And this is, the figure show us the average position of the SPCC, South Pacific Convergence Zone, where the South Pacific Convergence Zone is characterized by low-level convergence wind here, and between northeasterly wind west of the South Pacific High, and also colder southeasterly wind from the higher latitude ahead from high pressure, as we can see in this figure. This is very well known. There is two bands over the tropical equator. There are one is the intertropical convergence zone, and the second one in South Pacific convergence zone. And today I would like to focus in the South Pacific convergence zones. The South Pacific convergence, according to the number of previous study, that the SPCC plays an important role in climate in South Pacific, as mentioned by Vincent et al., and also suitable forming for the tropical cyclone, as described by the Lore et al. 2012. And moreover, the displacement of the SPCC can make a significant change of rainfall in the island of the Pacific region, including Indonesia, as pointed out by number of previous study. Then the Juliet 2006 study highlight that the increased frequency of the El Nino event from 70s until 90s led to increased response in the species. The significant influence of species on climate show the importance of understanding variation of the species characteristic. In addition, lack of study assessing influence of species on climate in Indonesia, so conducting the further study is necessary. The objective of the study is to examine the variation of the South Pacific convergence zone strength, convergence area, and also the orientation of the ice species. The second one is to investigate the relationship between this IPCC strength and Indonesian rainfall variability. So this study used the several data. Then we can see here zonal wind and meridional wind, total precipitation, ocean surface, and also precipitation data derived from the chips. So for this study, the species region is encompassed by 0 through 30 south and 130 east until 110 west. Then the strength of the species is defined by the surface wind convergence in this region derived from the grid data wind factor. Then we assess the species characteristic according to the Kitwell et al. 2016, which is there are 4 indices constructed by this characteristic. So divergence and convergence of the wind is derived from the data from the wind velocity, whereas divergence in divergence is calculated by equation. And the total area of a species is calculated by this one, and also the species strength is defined by monthly area weight average value derived from this equation. So we already identified the species by see this figure. We can see that the A, B, C, and D is the seasonal climatology for rainfall superimposed with the wind factor. We can see that the very clear pattern of the species here. Hello, can you hear my voice clearly?
Yes, please continue.
Okay, then I would continue my presentation. This is the South Pacific convergence zones. Is oriented diagonally tracing northwest and southwest from the New Guinea to the central subtropical Pacific. Then the species is a band of low-level convergent wind and resultant the precipitation and cloudiness, as we can see from this figure from 8 is the December, January, February. B is the June, July, August, and so on. Then in order to identify and assess the convergence area and also convergence strength, we use the data from the QuickScat and also the era interim. Then here, there is two figure. We can see that the mean structure for the two data set have similar, whereas the positive value are correspond to the divergence and negative value correspond to the convergence. The transition of the tropical and the subtropical regime we can see here the SPCC associated with the weaker convergence and having a larger tilt on the northwest and southwest direction. So the pattern can see here, the A is an era interim data and B is the QuickScat data. Why we compare this one? Because the QuickScat data is not longer available, but this is more representative comparing to the era interim data. Then here, we already constructed the indices for the SPCZ characteristic called the SPCZ area and also the South Pacific convergence zone, the orientation. Then there is two data here. The blue one is the QuickScat and also the red one is the era interim. There are similar pattern or there are good agreement between the QuickScat data and also the era interim. So we can use the era interim to further analysis of the more longer time scale of the IPCC strength area or also orientation. So this is the characteristic of the SPCZ. We can see here the seasonal variability, the time mean structure of the convergent and divergent from DGF until the September, October, November, range from 1981 until 2018, which is the positive value are divergence and negative value correspond to the convergence area. So the seasonal convergence here is stronger during the boreal winter according to data analysis and weaker during the boreal summer or as evident from the more negative value of the convergence in December, January, and February.
Excuse me, you have still have 3 minutes.
Okay, and the temporal variability of the SPCZ, we can see there are three indices here. The SPCZ area, and the second one is the latitude oriented, and also the longitude centroid of the SPCZ. Then the fourth indices, we construct the SPCZ strength from 1980 until 2018, we can see here the interannual variability of the SPCZ strength. Another good finding here, 1982 and 1997, where the strong El Nino, there are also strong the convergence. This result is consistent with a previous study which stated that the convergence trend and has significant negative linear relationship with the El Nino. Then by using this index, we make a spatial correlation with the SPCZ index and also Indonesian rainfall. We see here there are spatial pattern different between seasonal variability from January until December, whereas the January until April, there are positive correlation between SPCZ strength and also Indonesian rainfall in most part of the Indonesia. While from May until August, there are negative correlation we can see appear in almost part of the Indonesia. So what is we conclude from this research? The surface winds product from the atmospheric analysis and also from QuickSCAD data we used to examine the variability of South Pacific convergence zone strength, area, or also centroid location. The variation of SPCZ strength, area, and centroid latitude are dominated by the seasonal variability, with the SPCZ are having the stronger seasonal variation. And also we find that the strong El Nino and 82 and also 97 are associated with strong convergence, and this is needed to be further examined. The strength of SPCZ could have important implications since the South Pacific convergence zone is the largest rain band in the southern hemisphere and can affect regional climate. Even though we don't explain about the skillful of prediction, but we are going also investigating the skillful prediction of seasonal and interannual variability of the South Pacific convergence zone using output model. This could benefit use for utilize the seasonal forecasting information for decision making and many applicable sector. I think that's all. Thank you.
Okay, thank you very much, Dr. Rahmat. So because we have some very limited time, so discussion for Paramat maybe we will deliver for the end of this session during the discussion session. So thank you, Pak Rahmat. And then now we move to the third speakers from BMKG. So we have Dr. Urip Haryoko, the speaker. So Dr. Urip is the senior researcher from 2020 until now, and then he also the expert team of the data requirement for climate services for WMO, and also former director for Marine Meteorological Center from BMKG. So Dr. Urip will talk about the Indonesia readiness toward implementation of high-quality global data management framework for climate. So Dr. Urip, you have 15 minutes for presentation and then question and answer. So please start your presentations. Urip, are you ready now?
Okay. Good afternoon, everybody. I will share first.
Hello, Pak Urip. Okay. Urip, you have 15 minutes.
Yes.
Okay. Your presentation is already seen on the screen. So you may start your presentation.
Okay, thank you, Pak Erwin. Good afternoon.
You may start.
I said my presentation is good.
Yes.
Okay, thank you very much. Yeah, today I will present about the high quality data. Maybe this is a difference between with the other speaker because the other speaker talk about the tropical meteorology and also atmospheric science. But today I want to talk about the global data management or high quality data. In this presentation, I would like to invite the climate community to see how prepare the quality climate data for analysis and prediction as well as for research and national, regional, and global level. High quality global data management framework for climate was initiated by the WMO to provide the manual, guideline, and procedure to prepare the high quality data. I think this is a good chance for me to socialize concerning to the high quality data, which should be provided by the National Met Service and other institutions who hold the weather and climate observation. WMO as an agency that has the authority to regulate regarding to the weather, water, and climate has initiated to create this high quality global climate data management framework. Okay, this is my outline. The first, I want to talk about the high quality global data management framework, and the second, WMO's stewardship maturity thematic for climate data, and the third, all the Indonesia ICTMAS or data management for climate. My voice is there is tail voice. Please mute all the speaker, please. Okay. Where we need a high quality global data management framework. First, I think the climate is changing and data are helping address many challenges of adaptation and mitigation. So including the social economic implication of this change. The decision maker need reliable data product like statistical analysis, model output, observational data product, and climate prediction and prediction. And that the user need the high quality data, which easy way to access and based on the high quality. And the latter, the dataset maturity score can help to provide such information. Okay, what is the high quality data? The high quality data is produced based on the best practice. The important thing is the best practices of observation, data analysis, and model. So it's mean data is not only observation, but including data analysis and model. This is the data. And the second, the aspect of the high quality data is discoverable and accessible. So if we have some data, it's been said that the data is qualified, it needs the data has to be discoverable and accessible. Is it understood? And number 4, suitable for use in science. So if you have a data, it should be easy to use in science, decision, and policy making. Number 5, produced through the easily verified quality management process. So all the data need to be quality checked. Number 6, surely preserved, described with sufficient metadata. And the last, metadata is the information of the data is very important. So that for the user who use the data, they can know what is the information of the data. And now, what does the ICTMAS provide? There are 3 aspects that provided by the ICTMAS. Number 1 is and then a self-assessment tool, and also a catalog of climate dataset. So on the next slide, I will talk about the manual and self-assessment tool. How to assess our data with the assessment tool so that we can know about the stewardship of the management. Okay, I will skip this presentation. Who the framework of collaboration? The number one is National Met Service. I think this is BMKG and also the Regional Climate Center and also International Data Center, climate research bodies, certain government agencies, and also academia. I think all the institutions here join in this meeting as the collaborator of the framework. Yeah, this is the component of the HQGDMFC. There are three components. The first is manual of best practice and standard, and then the dataset assessment with the stewardship maturity metric for climate data. So next, I will talk about the stewardship maturity metric for climate data in Indonesia, and then the last, the catalog of assessed climate data. And on the data assessment tool, included how the data is discoverable, accessible, usable, authoritative, high quality, and well-managed climate data set. So we can look at the next slide. This is the manual of high quality CDMFC number WM number 1238. They include the managing data from various sources with data management requirement and also climate data set maturity assessment. So if all the institutions need to assess or need to manage and to provide the climate data set with maturity assessment, so we can look at this manual. So how to assess the maturity of our data? This is the diagram of the stewardship maturity metric for climate data. There are four categories: data access, usability and usage, quality management, and also data management. And for each category, there are 2 or 3 aspects. For example, in data access, so data must be discoverability and must be accessible. Okay, and also at the quality management, the data must be take in the quality assurance and control procedure, and also quality assessment and data integrity. I can report to the audience that the BMKG now implementing the quality management system for data and information. So this is in line with the WMO program, how to provide the qualified data and information. And next, this is the maturity assessment of climate data set. There are 5 levels, level 1, level 2 to level 5. For example, if the data is not managed well, so the behavior of the data is ad hoc. And then if the data is limited managed or not defined, so the data have on the level 2 or minimal. So for the level 5, this is optimum. All the data is measured, controlled, and audited by the auditor. Yeah, this is the level of maturity assessment. This is an example of the aspect for data portability. The data portability will be level 1 if the data use non-machine readable. And when the management data use the basic machine readable, so there will be level 2 and so on. This, for example, the example of the data portability. The level 1 is if the such as non-digital data. So if your data is only in paper format or absolute media, so it will be level 1. But if your data is formatted as binary data, so it must be level 2 and so on. So by this procedure, we can do the assessment by ourselves. Okay. So next, how the Indonesia have high quality GDMFC? I will talk about the objective and goal of Indonesia high quality data. Number first, self-assessment of national climate data set, so that the data come from BMKG have self-assessment, so that we can know the maturity scale of the data. And then after we do self-assessment, then we will increase the maturity scale level for some essential climate variable. After that, we can create the climate data that follow the 11 fundamental aspects below. 1, accessibility, data integrity, data quality control, and so on until usability and usage. Note that on the blue color, it was partially implemented in BMKG. But we should increase the maturity scale, for example, from 2 to 3, 3 to 4, and so on. Okay. After we read at the matrix or from some reference, there are some gaps in high quality data in BMKG. Number 1,
Excuse me,
still a lot of data in hard
still
copy
have
format.
2 minutes.
Yes. Okay. Still a lot of data in hard copy format like this. And also the data format is not entirely standard and uniform. And then the climate data is not fully integrated. And QC is still at level 1 and level 2. So we still require QC level 3. Okay, I skip this. This is example from the how to assess the data for radar-based precision climatology for Germany. This is some example. This is the aspect for the data access have level 2 because the data distributed via the National Climate Data Portal via SFTP and HTTPS. Downloadable in Mandechan, and so on. And I want to show you how the data from BMKG. This is Southeast Asia climate data set and assessment. Southeast Asia climate assessment and data set, or we call SACND. This data has come from the Indonesia and come from the Southeast Asia or ASEAN. This is the daily blended data and gridded data set. You can use or you can open at this website. So we have done a self-assessment for the data. For example, for the operational data management have level 3, and the data stewardship have 3.3 level. For example, the data access have score 4 because the data is comprehensive discovery metadata. The dataset searchable online, access provided with enhanced online data services, distributed via the national and regional climate data portal, and also downloadable in daily basis and per parameter, and so on. Yeah, this is my last slide. Next, this is the roadmap and way forward to get the high quality data of climate. Number 1, on managing data from various sources. So we have to do the data rescue and then data reformatting, parallel observation analysis. And the number 2, and on the data management requirement, we should do ICTMAS implementation for climate data and information, and also digitalization and data integration. And the last, for the maturity assessment, we should do self-assessment of national climate data set and increase the maturity skill level for some essential. Okay, Pak Erwin, that's all. Thank you very much.
Okay, thank you very much, Pak Urip. So you have 15 minutes and then I'll conclude. So thank you, Pak Urip. And then we move to the next speakers before we break the session. So I invite Dr. Adrian Matthew from the University of East Anglia. Dr. Adrian, are you ready for the presentation? Yes, okay, thank you very much. Dr. Adrian, you have 15 minutes for presentation, including question and answer. You may start your presentation starting from now. Dr. Adrian,
okay, can you see my slide?
We're still waiting for your voice.
Great.
We have some
Can you hear my voice?
problem
Yes.
for the voice.
Can you not hear me?
Yes, okay.
Yeah.
I guess we miss your voice again.
Okay, I've just unplugged my monitor. Can you hear me now?
Yes, sir.
You may start now.
Okay, thank you very much. Thank you, Erwin, and thank you to the committee for allowing me to present today. So I'd like to... Sorry, I'm getting a lot of feedback from someone here. That's better. Okay, so I'm going to talk on propagation and growth mechanisms for convectively coupled Kelvin waves, GCKWs. So as many of you know, CCKWs are eastward propagating weather systems. I'm going to analyze them using the method of Baranowski et al. 2016. So what I've done here is created a base point on the equator at 75 degrees east, shown by the green circle here and in later figures. And these maps show lag composites of trim precipitation anomalies. Excuse me. So the top panel is at lag -1 day, and then at lag 0 days and lag +1 day. And you can see the precipitation anomalies propagating eastward with time at about a speed of about 10 meters per second. The CCKWs are important. They occur throughout the tropics. They bring extreme precipitation to the maritime continent and elsewhere, and they're a component of the MJO. So the questions I'm going to be looking at in this talk are: how do CCKWs propagate eastward? And in particular, do they have the same mechanism as theoretical equatorial Kelvin waves? And also, how do CCKWs grow? Because theoretical equatorial Kelvin waves are neutral. They have no growth. can't do page 10 now. Okay. So I'm going to do this using the vorticity equation, which you can apply to dynamical fields, to wind fields on a single level. So here is the vorticity equation. On the left-hand side, we have the vorticity tendency. So that's the rate of change with vorticity, zeta, with respect to time. And then on the right-hand side, we have a whole load of different source terms which can change the vorticity. So first of all, red, we have the advection terms, horizontal and vertical advection. Then in blue, we have the vortex stretching terms. So that's the action of the divergence on both the planetary vorticity F and the relative vorticity zeta. Then in green, we have the beta term, the advection of planetary vorticity term. That's how Rossby waves work. And then finally, in pink here, we have the vortex tilting and twisting terms. And that's where you can take a vortex that's in the horizontal and use the wind field to tilt that up into the vertical. I've also allowed for this extra term at the end, epsilon, and this is the residual in the vorticity equation. So that this includes all the errors in the system, but also any sub-grid scale processes that aren't resolved. So this is the equation I'm going to be using to do my analysis. And I should point out here that if we're just looking at theoretical equatorial Kelvin waves, the only non-zero source term is the vortex stretching, the minus FD term. All the other terms are zero for a theoretical Kelvin wave. So if we just start with looking at a theoretical Kelvin wave, this is the dynamical structure here. So you can see the wind vectors are, of course, just in the east-west direction. There is no V wind in a Kelvin wave. And the zonal wind is a maximum on the equator, and then it decays north and south of the equator with a Gaussian structure. And that leads to vorticity pairs. So here we've got, with the westerly winds, we have a cyclonic vorticity pair shown by the shading, with positive vorticity north of the equator and negative vorticity south of the equator. And we also have a region of convergence shown by the blue dashed lines here, and that's between the westerlies to the west and the easterlies to the east here. And then this leads into the propagation mechanism for these theoretical Kelvin waves. So in this plot here, the vorticity is shown by the line contours now. So again, we have this cyclonic vorticity pair, positive north of the equator, negative south of the equator. And then the shading shows the either the vorticity tendency or the vorticity source from vortex stretching, the minus FD term, they're equal. And the key thing here is that we have a positive vorticity source, shown by the red shading, to the east of a positive vorticity anomaly, shown by the red line contours. So that will give you an eastward propagation mechanism for the equatorial Kelvin wave. So that's the kind of thing we're going to be looking at when we come to look at CCKWs now. So here's the dynamical structure of convectively coupled Kelvin wave. This is created using era interim data. I've done some wave number frequency filtering to isolate the CCKW signal. And again, we've got some lag composites here from day -1 at the top through to lag 0 and through to lag +1 day. And again, you can see the whole structure in the different fields propagating eastward with time at about 10 meters per second. So if we focus on the lag 0 structure, then you can see the wind vectors are pretty much all in the east-west direction. So the V wind is very small, so it's very similar to a theoretical equatorial Kelvin wave. Associated with that, again, we have a cyclonic vorticity pair shown by the shading here. And we also have a region of convergence between the westerlies and the easterlies, and that's to the east of that cyclonic vorticity pair. So initially, the structure does look fairly similar to a theoretical equatorial Kelvin wave. If we go ahead and do a vorticity budget, at the top of the screen, we have the vorticity tendency. Oh, I should say that in all of these diagrams, the line contours are the same. So the line contours show the vorticity anomaly, and the shading is different in each one. So the shading in the top panel shows the vorticity tendency, and we can see here we've got red shading showing a positive vorticity tendency to the east of a positive vorticity anomaly. So that's going to give us eastward propagation. And if we look at the vorticity source, the shading in the middle panel, that looks very similar to the vorticity tendency in the top panel. So that's good, because that means we've basically got a closure of the vorticity budget. And consistent with that, the residual is shown in the bottom panel. That's the difference of the top two, and you can see that's fairly small. So if we go ahead and look at the individual terms now, there's 8 of those shown by the panels here. Again, the line contours are the same between each panel. They show the vorticity structure of the CCKW, and the shading shows the individual vorticity sources, so that's different for each panel. So if maybe we start with the vortex stretching, the minus FD term, which of course is the only source term for a theoretical Kelvin wave, so that's this one down here. Well, first of all, we can see that it actually has relatively small amplitude. The shading is relatively small compared to some of the other terms. But if we look at the phasing, we can see that we do have red shading here, so a positive vorticity source to the east of the vorticity anomalies, shown by the line contours. So that is going to give us eastward propagation, as it does with a theoretical Kelvin wave. If we now look at the other terms, let's look at the other vortex stretching term, the minus theta d term to start with. But you can see that that's actually much larger amplitude than minus FD. And if you remember, if this was a theoretical Kelvin wave, all of these other 7 panels would be 0. There'd be no shading in them at all. So it's clearly very different to a theoretical wave. Okay, so this vortex stretching has large amplitude, but also if we look at the phasing, it's actually rather different. We have positive vorticity source, the red shading, pretty much in phase with the positive vorticity. And we have a negative vorticity source, blue shading, pretty much in phase with a negative vorticity. So that's going to lead to growth. Maybe this is a strong growth term. If we now look at the horizontal advection terms, here's the zonal advection term. Again, this is quite strong, and you can see you've got a positive source to the east of the positive vorticity anomaly, so that's going to lead to eastward propagation. But you've also got a large blue shading, so that's a negative source that's partly in phase with the positive vorticity, so that's going to lead to decay. That's going to destroy the CCKW. If we go on to meridional advection, again, here we've got a positive source, red shading, coincident with a negative vorticity anomaly, the blue line contour, so that's going to lead to decay. Let's move through the others. Here we've got vertical advection. That's in phase with the vorticity, so that leads to growth. And if we jump down to the tilting terms, one of them is basically 0. This one is 0. But this one here leads to decay. We've got a positive source in phase with a negative vorticity anomaly. And the beta V term, the Rossby wave mechanism, is as we expected, rather weak. So we can summarize the effects of each of these terms in this bar chart here. So each term is shown by a different color along the bottom. And I've got various diagnostics plotted here. So the top bar chart shows the root mean square amplitude, so basically the strength of the term. The second chart shows the spatial correlation coefficient of the source term with the underlying vorticity pattern. The The third one shows the entropy generation, so basically shows you which terms give you growth, like the minus theta d term, which terms give you decay, like the meridional advection term. And the final bar chart shows the phase difference between the source term and the vorticity pattern. So I'm going to jump ahead now and use this, the top one, the root mean square amplitude, and the bottom one, the phase difference, and plot those in this, what I call a propagation growth polar diagram. So just to orient you here, each term is plotted in this diagram. The radial coordinate, so the distance from the center, is equal to the root mean square amplitude, the strength of the term, and the angle where it appears, the azimuthal coordinate, shows you the phase difference between vorticity source term and the vorticity pattern. And I've oriented that such that if you're in this blue sector on the right, the source term will lead to eastward propagation. If you're in the blue sector on the left, it will lead to westward propagation. If you're in the red sector at the top, it'll lead to growth. And if you're in the red sector at the bottom, it will lead to decay. So first of all, the vorticity tendency, d zeta by dt term, that's right on the eastward propagation axis. And actually that has an amplitude of 1. I've normalized all the terms relative to the vorticity tendency. And you can actually see, I probably should have made it a bit darker, but there's a grey square behind that says EKW. That's the theoretical Kelvin wave forcing. And of course, that lies on this axis, giving you eastward propagation as well. So we should compare the terms for the CCKW with that. So you can see that eastward propagation in a CCKW is mainly due to this minus FD term, which is the same one as in the theoretical Kelvin wave. It gives you eastward propagation, it's in the blue sector, but it's also giving you a little bit of growth as well. And also the horizontal advection is just about lies on the edge of the eastward propagation sector. If we look at what terms lead to growth of the CCKW, well, by far the biggest one, it's the other vortex stretching term, the action of the divergence on the vorticity within the wave, the minus theta d term. And also the vertical advection term is important here as well. However, it's not just a simple case of growth. These are countered by these terms down here, which give us decay. So again, we've got the zonal advection term contributing, the meridional advection term contributes even more, and one of the tilting terms gives us decay. If you add up the effect of all of these individual terms, you get the total source term. That's shown by the purple circle here with a symbol S. And you can see where that lies in this diagram. It mainly gives you eastward propagation. It's in the blue sector, but it's above the horizontal line, so it gives you some slight growth as well. So because of this, and because of the contribution of minus FD to the total source term, the underlying result is that CCKW propagation growth is really like a highly modified theoretical equatorial Kelvin wave. So to conclude, convectively coupled Kelvin waves, their propagation and growth is controlled by the lower tropospheric structure. That was all at 850 hectopascals. The results are showing you there. The vorticity balance is basically like a modified theoretical equatorial Kelvin wave. I didn't get the chance to show you this, but the upper troposphere seems to arise as a force response to the lower troposphere. It has a very different vorticity balance, nothing like a Kelvin wave at all. So this is a new technique, and I think this can be applied to looking at forecasting of CCKWs in NWP, simulation and climate models. That's going to depend on getting the correct propagation growth mechanisms, and this would be a useful diagnostic for that. So there's plenty more to do here. What I'd like to do next is incorporate a thermodynamical balance in addition to this vorticity balance. I haven't talked about convection at all, and we know that that's important, and the role of moisture, so incorporate a moisture balance into this model. I picked the central Indian Ocean just for this analysis because it gives a nice, strong, clean signal, but I'd very much like to apply it to other locations. So the next one, I think, over the maritime continent itself. As I said, we can apply this process-based diagnostic analysis to NWP and climate model output to understand the model errors there. And then finally, this is quite a general technique that I think can be applied to other phenomena such as other equatorial waves and the MJO itself. So it'll be interesting to do that in the future. So thank you very much for your attention.
Again, after 4 presenters, so now we move to the break session for 5 minutes. And then I hope all the floor can write down some question and answer on the chat room. So we will meet again at next 5 minutes. So please take your coffee or tea before we meet again in next 5 minutes. Okay, see you.
Basic sciences have had a very important role in the development of science and technology. The Bogor Agricultural University, now called IPB University, in 1979 pioneered the establishment of the Faculty of Mathematics and Natural Sciences as a foundation for the application of sciences in IPB and as an effort to develop relevant science and technology to utilize and manage resources for people's welfare, mainly related to agriculture, marine, and tropical biosciences.
Visi kami menjadi fakultas bidang MIPA yang terkemuka di Indonesia dan bertaraf internasional.
The Faculty of Mathematics and Natural Sciences, known as FMIPA IPB, is located at the Dramaga campus, Bogor Agricultural University. This faculty has 8 departments from various different disciplines. This faculty organizes educational programs from bachelor, master's, and doctoral levels under the guidance of a competent teaching staff according to their respective expertise. Various collaborations both at national and international levels in the framework of research, human resources development, and community service are held regularly and periodically as a form of realization of the 3 pillars of higher education mandates.
Science for community, mediation, and prosperity.
FMIPA IPB is more than basic science.
maritime country in the world, we are aware of the importance of our ocean in influencing the world's weather and climate, especially the influence of the Indonesia through flow connected between the Indian and Pacific Ocean to the weather and climate states in the world. Indonesia, through the Agency for Meteorology, Climatology and Geophysics, BMKG, is strongly committed to contribute to the safety of human activities and community welfare by continuously educating people on the importance of ocean weather climate literacy and sustaining our observation, and keep strengthening our provision of the accurate maritime weather and climate information, as well as early warning of the coastal disaster information such as storm surge, tsunami, and sea level rise to the community in Indonesia and in the region. Happy World Meteorological Day of 2021. Let's strengthen our partnership for the better ocean weather climate information.
Hello everyone. So now we meet again, and then I hope you already refreshed after you enjoy your coffee or tea after the break session. So in this second part of the session, we still have 3 speakers. So after the three speakers, so we will continue with the discussion and then some question and answer. So in this session, I would like to invite Dr. Erma Yuliastin from Lapan. So I hope Bu Erma already ready now. So you have 15 minutes for presentation and then question and answer. Bu Erma, you will start your presentation from now. Okay, please.
Thank you very much. Our voice is clearly? Okay. I want to share my talk first. Okay. Okay then. Thank you very much. Pak Erwin, give me change.
So,
hello.
I guess your voice is not so clear. Maybe you have to set up again, setting your voice again.
Sorry. How about now?
Bu Erma, we still miss your voice.
It's delay, I think. I don't know why. Can you hear my voice?
Okay, okay. You may start now.
Okay. Thank you very much. I hear my feedback voice. Are you? Hello?
Yes, Bu Erma, I think your voice maybe not so good now.
Yeah.
Do you have some obstacle or something to set up?
Sorry. I don't know. For my side, is already fine.
Maybe you have some signal, internet signal also.
Yeah.
Okay. I think now your face is good. You may start. I think now your face is good. You may start.
Okay. Please talk to me if my clear is not. Thank you very much. I'm Erna Yutastin, research scientist from Lapan. Today I want to talk about of early morning and the quality of the northern coast of West Java. So the first of all, I would like to acknowledge my college from ITB for so this research is already sick, and the second part I'm sorry, can you hear my voice clearly? Or maybe I left first and I will join it again. Sorry, Pak Erwin. Have I need to join again? Because
Bu Emma,
voice.
Bu Emma is.
I think I need to stop.
Bu Emma. Yeah, maybe
First and join
I
again.
think your internet signal maybe not so stable. Maybe may I ask you to skip your presentation, and then maybe you have time to just to repair your connection, and then maybe may I ask your permission to go to the next speaker. We'll back to you again. And for the next speakers, so I invite Dr. Gert Jan Steeneveld. Okay, I'm sorry, I cannot. Okay, Dr. Gert, are you there? You still mute? Yeah, okay.
Yeah, okay. I'm there. Yes, I'm ready for it. I will share my
start now. Thank you.
Slides. Let me see. Full screen. Yes, there we are. So I hope you can hear me well.
Yeah, you may start.
I hear me well. An echo. I hear myself back, which is a bit annoying, but I will just continue. So I will just continue. My talk will be convection or waste, but more about neither talk about convection or waste, measurement techniques that can be applied at measurement. It talks about colleagues from different universities in Delft, Wageningen, Kenemaai, with whom we worked on this project, and it is about crowdsourcing. So how can we use smartphone data and other crowdsourced data to work? So how can we use get valuable meteorological information? Data to so we introduce meteorology, use a bit the so-called smartphone technology. Well, there are many devices nowadays around, and devices are data. And there are smartphones. They contain direct sensors for temperature, relative humidity, light, and pressure. direct sensors, but also smartphones. We can extract information from indirect observations like battery temperatures, items. So what we discovered some time ago is that we set up a model that if you have a smartphone, I hope you see my mouse. If you have a smartphone, it runs at a certain power P and has a certain temperature TP. Then it might be dangerous if the smartphone becomes too warm for the health of the smartphone. And well, there was a company, Open Signal, it's located in the UK, and they earn their money with checking network connectivity. So you can, on your smartphone, you can install this app, and this app checks for you the connection, whether the connection speed capacity is as much as your provider promised you. But it also logs the battery temperature of the smartphone. And well, we thought, okay, can we relate this smartphone battery temperature to the weather outdoor? Little model for that. So we say, okay, we have this temperature of the smartphone, and via heat conduction between the body and a certain clothing layer, KB, and we have a connection to another clothing layer to the atmosphere. This is KE. Can we then estimate the air temperature purely if we have the battery temperature? So, and it appeared that we have we can build a little regression model. So the estimated air temperature for a city as a whole, so we aggregate many smartphones, is related to a coefficient M that is based on those KE, and KB, so the isolation by the clothing, the temperature of the smartphone, and the temperature of the body. And what happens then? So this is a result for Sao Paulo. Yellow line are the battery temperatures that were recorded, and blue lines are the observations from the local WMO station. What you see is there directly that there's a coincidence between high smartphone temperatures. You will directly see them also connected with high air temperatures, for example, here. So that is a good estimate or a good indication that there's a connection between the two, and that we can use them the other way around. Like if we have the smartphone battery temperatures, then we can use that to estimate the air temperatures, especially in cities where normally we do not have so many measurements. So the result of our model is the black line. And you see that with the model, after calibration, of course, we can have a relatively good estimate of the daily mean and citywide air temperatures. Well, that is of course promising, but only a first step, because who is interested in daily mean temperatures and citywide temperatures? And the goal of the study is also a bit to zoom in further. Can we go spatially in more detail? So here we look at the map of Sao Paulo for the half year data that we had, and each blue dot is a smartphone temperature record. So you see there's a massive amount of smartphones available, and we have some reference stations. These are the red, white, and green one from either hobby meteorologists, more expensive Davy stations, for example, and the airport station from the WMO station over there. And what we would like to do to aggregate kind of air temperatures now, not over the city as a whole, but over local climate zones. So building structure that are kind of similar. So the most dominant one in Sao Paulo are so-called local climate zone 3, which looks like this. So it's heavily built, there's hardly any grass, but it is low rise, not more than 3 stories. Then we have the local climate zone 6. So this is relatively more open with green. That is the red here, so it is very abundant. And we have large low rise, that's what they call it. So this is typically this kind of industry park with services. And these are the gray ones. Well, if we aggregate then the smartphone data, not over the city as a whole, but according to those categories, the building structure, we see the following. That taking the WMO station in the middle of the city as a reference, then we see that the urban heat island effect for the different local climate zones can be distinguished with a clear smaller urban heat island effect for the local climate zone 3. and a relatively larger one for local climate zone 8. So the low weight industry park, they really have a higher urban heat island effect. So this means that going from citywide estimates, we can also go down further into the spatial detail and distinguish urban heat islands effect in different local climate zone. And you also see here the full data set, and for local climate zone, we can reach quite high scores just with free data. Well, now we do a little calibration. So we want to move on to hourly values. So we take the same models, but now we calibrated it to 24 M values during the diurnal cycle. And then we get this signal. These are now for the month of July, so a much shorter range. The diurnal cycle modeled, that is our black line, and the smartphone, the validation, so the observations. And you see there's a good coincidence in general. The model has some problems with cold nights, as you can see, and we will see that later on. That is not unique for Sao Paulo, but it's also appearing in, for example, Amsterdam, because that's my next slide. So we did the same exercise for the city of Amsterdam in the Netherlands. So here each red dot is a smartphone record. Here we also had about 1.5 million smartphone records only for 1 month. So this is the month of June. As you can see, well, the red line here in the graph is the official Kenemer observation data record taken at the airport. And our smartphone estimate from the air temperature with the battery is the blue line. And now you look at the hourly values, you see more scatter. But in general, especially for nice summer days with the good diurnal cycle, the modeled signal is quite good in following the observed signal. And you see also that at night we have problems. The model is typically underestimating the temperatures, and that is likely due to the fact that we have less smartphones available, of course, because people are asleep and their smartphones are switched off or loading, charging. Well, what else can we do with these the other sensors, for example, because we do not know whether the smartphone is carried by somebody in the pocket or a handbag by women, for example, whether we are indoor or outdoor. So we're looking for techniques to check whether the sensor, the smartphone is indoor or outdoor, because we want to focus, of course, on outdoor air temperature estimation. So then we correlated the illumination, so the signal from the light sensor in the smartphone in blue here versus the global radiation incoming at Schiphol Airport. And then you see there's a quite good coincidence. The diurnal cycle is followed rather well. And well, you see in some days the coincidence is better than other days. And I had a bit of impression that this is because of weekend days. People are more outdoor, especially in summer, and then the correlation is better. So it means that in some days we can estimate with this signal whether persons are indoor or not. But on other days it's a bit difficult. It's not really decisive yet. But we ask ourselves the question, can we also estimate cloud cover using those smartphone data with the light signal? So here you see at the diurnal cycle, we look again at the same month of June 2015 in the Netherlands. The cloud cover, the observed cloud cover is on the right axis, and we distinguish between two typical days. So the orange line is the 18th of June, which is kind of fully clear sky day with 0 octa. And then we try to estimate what is the smartphone line the smartphone light sensor giving us, and that is the orange line for that day. Well, it gives a very clear diurnal cycle with a high solar peak, or a peak in the solar radiation that is observed. And if we compare that, for example, to the 9th of June, and there we see that the observations we have till noon, kind of, we have a fully covered sky, then some scattered clouds. And it's also reflected in the smartphone sensor, because the blue line for that day gives a much lower signal than the clear sky day. This gives this is an indication that we can indeed use this light sensor from the smartphone to estimate cloud cover. And well, the other green lines are the other days in June that we do not really verify, but then it gives you a kind of an impression what is the typical variability in the diurnal cycle of solar radiation that we can estimate with a smartphone. Well, this is all nice, and we use smartphone now, or many smartphones together, kind of as a proxy for temperature measurements. And we often get critics or questions like, what is the ground truth? So what we try to do is that we tested the smartphone, in this case, Galaxy S4. We mounted it on a cargo bike here, which is act as a reference station, and we cycle trajectories through the countryside, but also through the city, and kind of cross-compare what is the smartphone sensor giving us and what is the professional station on the bike giving us, and how does this compare. And also we put the smartphone in a traditional Stevenson screen and compare them with the observations from the two devices. So what do we get? If we look at, this is a part of the trajectory that we are cycling, so the air temperature. This is a winter day, so the bike gives us the black signal, and the blue is the smartphone record. And you see that there is coincidence in, for example, a relatively warm peak in the bike is also a relatively warm peak in the smartphone, and a cold episode in the bike trajectory is also a cold episode in the smartphone track, but you also see that in color. I plotted here the amount of solar radiation that the smartphone has the tendency to overestimate, or at least the signal is amplifying when there's more solar radiation. So in general, the smartphone is giving a cold bias here, about 1.5 to 2 degrees. But the bias depends on the solar radiation. So we have to correct for that. So we built a table that the smartphone bias compared to the professional station depends on the wind speed here and on the solar radiation that comes in on the x-axis. And well, you see a clear gradient that for low winds and low radiation, the bias can be -4 degrees. And for high solar radiation, that's and high winds, or even for lower winds, it's even worse. It can be +10. Well, this is of course a bad news, but on the other hand, we can use this table.
Excuse me, you still have 2 minutes.
Yeah, thank you. So this table gives us also an indication to kind of build a correction scheme, just to calibrate the observation, the smartphone observation. That is what we did. So this is what I do here is I compare for our city of Wageningen. So the university campus is over here, and the bike temperature is the reference one here. You see quite variability in temperature. Here's a little bit warmer. So this is also the city center. It's not the middle of the cities, but the city center where we have, let's say, the shopping malls and that kind of activities. And the relatively cold areas in the neighborhoods and the outskirts of Wageningen. Now, if we then use the smartphone data record that we had, plus the correction scheme that we developed based on this table, you can still make an estimate of the temperature in the trajectory, and then you see that we kind of do a relatively good job. There's quite a good coincidence between the warm episodes here again in the city center, the relatively cooler spots on the university campus, and also the cooler neighborhood here is being seen by the smartphone sensor after correction, of course. So what did we learn from this presentation? Well, the smartphone data can provide valuable insight in the urban atmosphere because we have free data. Well, after data selection and processing, we can make estimates of the urban heat island. For example, we could do that initially for citywide and daily mean temperatures, but we show that, well, if we zoom in local climate zones, for example, we can also spatially increase the resolution. And the second part was, okay, we can also do that for hourly values with hourly calibration. So that helps us a lot in getting more detail. Also showed some results from the light sensor. We estimated cloud cover with this quite successfully, and we're still working on how to use this light sensor records to indicate whether the smartphone is indoor or outdoor, so we can better filter smartphone records that we want to use or not, because we want to focus on the outdoor temperature records, of course. And finally, I show that, well, we have those smartphone data and they have a bias, but if you correct them for the bias that depends on the wind speed and the radiation, then you can still reproduce quite correctly the temperature trajectory through a city. And that's what I wanted to share with you. Thank you very much, and I'm happy to answer questions.
Okay, thank you, Dr. Gert, for your presentation. So your discussion maybe will be delivered in the end of the session. Okay, thank you, Dr. Gert. And then for next speakers, I invite Dr. Paul Davis from UK Met Office. Dr. Paul is currently the Met Office Chief Meteorologist and Principal. Dr. Paul, are you ready for the presentation? Hello, Paul?
Yeah, good morning, everybody.
Hello, Paul?
Hi, good morning.
Maybe you still mute you may test your microphone. Paul, would you please turn
My
on
microphone
your
is
camera?
working, I believe. Hopefully I should be.
Oh, yeah, okay.
Good morning.
I can see you, but we still cannot hear your voice. I miss your camera again.
Hopefully you can hear me now.
Okay. Okay, will you please to share your screen now?
I'm hoping you'll be able to see my presentation. Can you see my presentation?
We can see your screen. You may start now.
Thank you very much. Yes, good afternoon, everybody. My name is Paul Davis. I am the Chief Meteorologist and the Principal Fellow for Meteorology at the Met Office. What I'm going to try and do this afternoon is consolidate in 15 minutes what's taken us about 20 years to develop, and that's impact-based forecasting and warning services. And I've had the pleasure and privilege of leading some of these activities around the world. And I want to just give you a narrative, a history of how we got to impact-based forecasts and warnings, and to give some indication what the next steps could be. So it started really in France in 1999 when there was a major windstorm that hit northern France, in the Netherlands and in Germany. And these two storms were hugely damaging, unfortunate loss of life. And to be from a meteorological perspective, we were a bit slow in terms of picking up these developing these windstorms, and the warning time from issue and when it impacted was shorter than we would wish. And so we in France we reviewed the warning systems at the time in 1999. This is 20 years ago, and what we discovered that even though we're slightly short in terms of the lead time, the forecasts were generally good. So the quality of the forecast itself wasn't the real concern. It was the uptake. It was the poor efficiency and understanding of the warnings that resulted in the review and the changes in France that led to eventually the impact-based warnings that we now provide across most of Europe. And out of that particular event, Meteo France developed a vigilance warning service. And they spent a lot of time with social scientists, talking to the users and customers of warnings, and asking them, how best do you want to receive warnings? And out of that analysis, they said simplification and appreciation of what that warning means to me as a person. And in terms of colors, that resonates to me better than the words. So it was more sort of graphical representation of warnings, which came out of that social science review. And so Meteor France then developed these color codes from green to yellow to amber to red to signify the level of vigilance that required based on the warnings issued. So green means it's all clear, there's the business as usual warnings. And the red means there's an alert. It means there's to take action. We need to take action because there's a warning that suggests that the threat is potentially life-threatening. It's interesting now looking back at this time and being involved in various reviews of warning services. The colours you probably don't want to mess up is the colour green and the colour red. And the reason being because if you're colorblind, then you find it very difficult to distinguish between green and red. So in China, for example, they have changed the green to a blue color. So, you know, it was a good start in terms of the vigilance warning system, but we have also developed our services since the time we introduced that. And now, and I'm the chairman of a Meteor Alarm group, which is a UMetNet collection of 37 national Met services, who now provide the warnings for all the countries across Europe. And this is a snapshot of one particular day where you can see majority of Europe is under green conditions, which is business as usual weather conditions, and the colors then going from yellow to amber to red, and red signifying in this case of life-threatening and potentially property damaging warnings and threat to life. So in that context, it's really advanced. And you'll notice too that we're not only do we issue warnings based on weather, but also issue warnings based on hydrometeorological conditions and also geological conditions as well, such as landslips, landslides, and avalanches. So it's become almost getting to the point of multi-hazard warning capability that we have now developed across Europe. So that's all good. And then I was asked to join a UN task force to go to the Philippines after Haiyan in 2013. And the question was from the UN was, why did so many people die? And I was privileged to go with UN colleagues, with universities, and we met a lot of the local community and met the authority agencies who prepared for Haiyan. And what was striking of Haiyan was, again, the forecast was fairly good. In terms of the surge, it was remarkably good. And the surge came into, if you recall, to the city of Tacloban. The problem is that the warnings which went out talked about a storm surge. And when I went to Tacloban and asked the community, did you understand the word storm surge? And the response was overwhelmingly, no, we don't. They were saying to me, if you had described the warnings as a tsunami, then we would know what you mean and we would take action. But because you use the word storm surge, we don't understand what that term means. And so therefore we didn't take any action. And so it came down to communication. It came down to appreciating what language and what ways we want people to take action based on a life-threatening event like Haiyan. And also here, I've taken a picture here in Tacloban, which was a sign that was put up by the government. And the word here, which is missing, is called no. So the local community said from the government, no build zone, don't build here. And they took the word no because they said we have no choice. Our livelihood is the sea. We have to stay where we are. So our vulnerability and exposure for the next typhoon has gone up. And so from that, we set up a task force, and I was the chairperson of this task force about developing an impact-based warning service. And there's guidelines now from that activity, which is now freely available around the world, which I was the lead author of, and contribution from a vast number of organizations, including the World Bank and United Nations organizations as well. So the question is, what do we do next? What can we learn over the last 20 years? And how do we move forward our warning services as we move into a warming climate and more vulnerability and exposure thereof? And this was a survey which we did within UMetNet of the 37 countries that contribute to that. And I think this is quite an insightful analysis, because what it shows you is a table starting from the hazards, which then includes the vulnerability. So in other words, if the hazard could be flood, the vulnerability could be the state of the roads to flood, and then the exposure is the people using the road. So how exposed are you to that particular vulnerability and hazard? And when you combine all those three together, you get an impact-based, risk-based warning service. And if you look back how you deliver that, you can start with a fixed threshold based on the hazards. So that could be 50 millimeters falling in one day. If that threshold is being breached, you issue a warning. It's fixed. Climatological based thresholds means that you look at the climate, you look at past events, and from that you could say, well, at 50 millimeters falling in 1 hour, in the early hours of the morning, we know we can lead to quite a lot of damage. So it's a climatological based thresholds. If that threshold is being exceeded, you issue a warning. The impact based warning is you go one step further. You say 50 millimeters falling in 1 hour, and that leads to disruption to the road network. You expect flooding property, and you expect some damage to other infrastructure, key infrastructure. So you're relating an impact to that threshold, taking in vulnerability. Impact-based warnings is now include exposure, you include people. So in this sense, you say the roads will be disrupted because of flooding on the road network, and you don't include the meteorology. It's an impact, pure impact-based warning. It's impact warning. So it's saying that the impact is the first thing you mention in your warning. And then we ask the countries, where are you on that scale? 5 years ago, the majority of countries are issuing warnings based on climatology-based thresholds. Now, again, a good proportion of delivering that similar type of warnings, but it's gone up. But you notice the impact warnings now gone from 13 to 31%. What they say in 5 years' time is that majority of countries are moving towards impact-based and, interestingly, moving towards impact warnings. So there's a definite shift away from fixed thresholds to impact-based and impact warnings. And largely that's a response from government, local communities and people for better understanding what does the warning mean to me. And the other thing we need to do is to be aware of, as we develop our new warning services, to ask local communities after each warning, how did it affect you? Did you understand the warnings? And what we do in the UK is every time we issue a warning, we have an independent questionnaire to the local community, and we ask questions like, do you understand it? Where did you get the information from? What action did you take? And this is really, really important as we go forward in the next development of warnings, because there's some things which I did at the beginning, I wish I hadn't. I wish I hadn't used the word take action for the red, because take action should be appropriate for all the color of the warnings, not just for red. And so by asking what action people take, did you take any action for anyone else? Was the warning useful? What did you do? 90% in this case stayed at home. This information is critical. The other bit as well, as you go forward, is taking the lost damage after the event from insurance, reinsurance companies, from other organizations, and then equate that to the warnings. So we better understand and quantify the impact of the hazards against the warnings we issue and try and make that improvement based on that information. And Sena has done a fantastic job in Indonesia in developing a starting process of recording hazards so that we can then relate that to warnings and event records. The other bit I want to talk about, I've got 2 more slides, is the future and big data and digital twins. And the phrase here is drowning in data, starving for information. In essence, we have so much information, well, not so much information, but so much data now flowing through all our systems. And it's often very difficult to disentangle that and get the insights we need to produce the warnings. And so the role of us as humans, along with artificial intelligence, machine learning, I think is going to be a critical way forward in improving our impact-based warning services. And that involves better recognition of the types of conditions that lead to the impacts we can see. So we saw in Jakarta in 2020. The humans will have have a good way of really unpacking some of that understanding that comes from the data and how we translate that into impact. And I think this is the critical bit as well. We need to embrace an environment that engenders co-creation, co-design, and collaboration. In that, as a meteorological community, we cannot do this on our own. We understand that. And we need to embrace other partners, other people of expertise that enable us to take that journey from a threshold-based warning service to a truly impact warning service. And that has to be and can only be done through a genuine partnership. And this is my final slide, because I was, again, honored to be leading the Coastal Inundation Forecasting Demonstration Project in Indonesia. And that is in response to the coastal inundation events across Jakarta and Semarang. And through that process, and with Nelly, who's been a fantastic leader in establishing this, is building a partnership with other agencies across Indonesia. And by collating and talking to each other, sharing best practice, we're able to provide a better service, I believe, to the local communities on the threat of coastal inundation. And this is the start of many, many initiatives, many opportunities. And that, I believe, is the way forward. The next steps in producing improved warnings is through partnership working. And that is something which Indonesia is certainly leading the way as we speak. So that's my presentation. Hopefully that sort of introduces some ideas, some questions, some thoughts. But I believe we're having the final question session later on. But thank you very much for your attention, and thank you very much for inviting me.
Okay, thank you, Paul. I think it's very interesting presentation. Also, you saw us the cooperation between UK and then also BMKG. So I think this cooperation will be continue for the future. So
thank you.
Again, thanks for Paul. So for the last speaker, so I hope Bu Erma already joined with us. So Bu Erma, we are very happy to see you again in this session. So I hope you can present your presentation for 15 minutes. Bu Erma, hi, how are you?
Hello, thank you.
Okay.
Can you
Bu Erma, you may share your screen.
Now? Yeah. Okay, I want to try to share my course. Yeah, my slide first. Okay, you can hear and see clear?
Yeah, okay. Bu Erma, you may start from now.
Okay, thank you very much. And I'm sorry for inconveniencing of my presentation first. Okay, hi everyone. I'm Erma Hastin, research scientist from Lapan. I want to talk about propagation convection system of early morning precipitation peaks, so-called EMP, over the northern coast of West Java. So this is actually our published research. First part, and the second part we under review in GMSG journal. So the EMP, what is the EMP? How significant of EMP? This is a very hot topic in Indonesia right now because we experienced with the big flood in 2020 last year, and this is associated with rainfall, extreme rainfall related to the EMP and associated with the TAMS. TAMS is cross-equatorial northerly surge, okay? And we see here Sadewa. Sadewa is basically an NWP operationally in Lapan, and we are running hourly and 2 days prediction, three days prediction later. From 2000, at about over 10 years later. So this is captured. The EMP is captured by the Sadewa, elongated over coastal region, and its background wind from northerly wind. It's very strong here. You can see here, and recorded by BMKG at about over 300 millimeters per day occur over Jakarta city and a big, greater area of Jakarta. Bekasi, and so on. So the repeatedly of phenomena is occurred again in this year, and we still remind of this phenomena, which is in 20 February to 2021, it's recorded 200, almost over 200 millimeter per day. And Sadewa in 1 kilometer spatial resolution also can predict it accurately before the chance hits and make extreme rainfall over Jakarta. So this topic is mainly about a diurnal pace problem. Okay, I want to mention here, it's about coastal precipitation, because in previous study, Ogino have mentioned about precipitation that almost concentrate over coastal region. And the EMP is very early in timing of peak of rainfall over coastal region that was detected over northerly coast of West Java, this our study area. And besides that, we define the two phenomena that probably can influence the background condition for the EMP. What's the phenomena? The first phenomena is about TEMS, northerly wind, defined by Hattori et al. About a strong northerly wind over this box, a green box. And SCSCT is South China Sea, cold Tang, is ocean phenomena, which cold of the sea surface temperature occur over this, that the SIF, the impact is SIF, oceanic precipitation. So we next move to the next slide. So what about the coastal precipitation and the EMP? Because in previous study, the EMP did not mention or did not capture as a propagating signal, because coastal precipitation characterized by starting from 10 LT, and the EMP is not captured over from this study. But Renggono et al. In previous study can capture the signal of EMP from the radar data, composite radar data, climatology. This is occur in secondary peak of signal of EMP from cloud activity. So let's try to identify the EMP first before we make a simulating in numerical study to identify the mechanism processes background develop the EMP. So this is the data we use in this research, and the EMP is identified from 1 until 4 LT. So the next step is I want to understand or identify the EMP clearly from the month-to-month variation and climatology data. And we see here that the secondary peak of precipitation occurred just in January and February over the coastal region. So I want to understand more about this signal, and I make analysis of Hofmöller. But in Hofmöller, it's not captured about the maximum precipitation in early morning. So I need to more detailed analysis because I want to understand is the EMP is significant. So I need harmonic analysis to derive this. And the harmonic analysis, we can see here that the frequency of EMP is significant, okay, for the morning precipitation at about 42%. And you look here that the amplitude of harmonic analysis have large compared to other type of rainfall. So the next question is about have EMP large amplitude and frequency? How about that? So I want to make an analysis, more furtherly analysis, and make a distribution of the frequency, accuracy, and mean amplitude here, And we can see here more clearly that the EMP is have base of amplitudes occurrences here. So the gamma distribution is a half signal that the timing of EMP must be randomness. Okay. And how about the large amplitude here compared to other type? This also make a signal that this is proof a significance of EMP for frequency and amplitude. Okay, now what about the relationship with extreme precipitation? So we see here more clearly about the composite of general cycle precipitation. I draw by 300 and almost 400 data, significant rainfall, yeah, climatology, and we see that the EMP is concentrated over coastal region. And what is interesting more is about the propagation. Okay, the propagation is look very clear from there are land propagating from the inland, but after concentrate over coastal region, it's look like that the propagate tend to land again. So what about the extreme? The extreme is captured by this. The EMP is very significant related to the extreme because the significant are the maximum precipitation in EMP concentrate over coastal region compared to the other type of rainfall. This is concentrate over land, and this is not to maximum rainfall over coastal region. So this is a very associated improvement for the extreme event related to EMP at about 40 sample of data. So now what causes the EMP? Because the background condition I mentioned before about SCSCT and chance, so I make calculated with statistical value, and we can see here more clearly that the chance and SCSCT very clear over these EMP samples. And if we see here that the green is EMP is almost distributed over this extreme diagram. So it's answer about the relationship with chance and SCSCT. So the EMP is very close relationship with two phenomena, which is induce the background condition of the EMP. So this is just for make more clearly between EMP and other type, and we see here that when EMP occur, the code of SCSCT clearly appear in here. So the next part is about, we understand that the EMP event should be largely determined of two factors. First is about location of the initial convection, and the second one is about direction and speed of propagation. So we want to understand more about the physical processes related to those key factors. Then we try to apply the numerical study to answer that. So the second part is about how about affect the background wind for the EMP. So for the sample of EMP and other, we have almost 50 sample of EMP, and we try to make composite here. And we separately by strong northerly, weak northerly, and southern northerly. And the red box is we define background wind, because in red box here, we propose that very influenced and very close related with the precipitation over coastal region in West Java. So we try here. And if we look at the more detail in here, maximum precipitation occur in strong northerly and also in weak northerly, and is here, like here. So the initial convection show the different pattern between three types of background wind. So I try to make more detail about this and make a simulation from WRF NWP, and make 3 samples as represented by strong northerly, weak northerly, and southerly. Strong southerly. This is from the model result. Each of the simulated event agree qualitatively despite some discrepancies. Okay, so we understand more about the process about EMP under strong northerly. We call it about landward cold pool because we just look here that the initial convection has developed from 0 LT, but quietly rapidly move and decay in here in 1 LT. And you see here that the anomaly potential temperature, the cold anomaly of temperature potential occur here at about 0.5 kilometer. This in our interpreted, we call it cold pool, okay? And the cold pool is propagate here. And you see here that this is clearly about mechanism of backbuilding. And backbuilding is thunderstorm that, characteristic of thunderstorm that appear in mesoscale convective system. So we see that we can identify cold pool here in landward propagating of strong northerly. And we look here that the resampling of backbuilding mechanism is very clear identified from this simulation. And how about the speed? The speed is about 12 meters per second, okay? So the next type is about offshore cold pool. How about offshore cold pool? This is not too strong compared to strong northerly, but we see also here that cold pool is developed here, developed here in 22 LT, and we see that the propagating of cold pool is not induced the new convective cell, okay? And how about the propagating? It's more slower because it's just around 5 meters per second. Okay, and let's move to the tree type, okay? This is the tree type. This is, this is a landward cold pool from the weak northerly. This is complicated mechanism because a deep convection appeared at here, in 20 LST, and decay we see here decay of convective fluid making cold pool again and propagate to the land, okay? And how about the speed of cold pool? Yeah, speed of cold pool is about 7 meters per second. So hereby we can confirm that the TP propagation or cold pool propagation and advection by the background wind is a plausible mechanism for the propagation convective system associated with the EMP event. So how about the rule of gravity wave? We considering the rule of gravity wave because in first cold pool, in landward cold pool, initial convection occur here. And we try to make drawing
very limited time, so
zonally and meridionally
to conclude your presentation.
Like here. And we see here that the layered structure of temperature anomalies become disrupted. So we see in near surface occur the signal of wave-like propagation very clearly. And when the peak of convection occur, the signal of wave gravity is disrupted. So here when we show that the possible influence of zonally propagating gravity waves is the initiation of convection offshore over Western Java. So this is our conclusion. The first of all is we understand that EMP has a significant frequency and related to extreme rainfall event and characterized by offshore as well as landward propagation, flat pace distribution, and large mean amplitude. The flat pace distribution of EMP that the timing of coastal precipitation is not necessarily locked to the pace of the land sea breeze, thus allowing the precipitation to occur more randomly. Furthermore, the role of STS-CT and chance as influencing factors for the occurrences of the EMP event. We also identify the cold pool that is generated below decaying convective clouds induce new convective cells near its leading and or trailing edge while propagating, and affected by background wind, which is respect the speed of CP is 5 until 12 meters per second. The mechanism involved in development of initial convection is the propagation of cold pool, and it has been demonstrated that sea breeze and gravity waves may play important roles in propagating convection system over the coastal region. So the recommendation from this research is we need an accurate short-range NWP to anticipate risk weather-related hydrometeorological disaster, and we have planned to improve the resolution of spatial of Sadewa for Indonesia from 5 kilometers to 1 kilometer and 200 for West Java with this design of setup. Okay, thank you. Thank you very much. That's all for me.
Okay, thank you very much, Bu Erma. So for all speakers, so we can see many questions in the chat room. So may I ask your response for 1 or 2 minutes for all the questions? So I starting with Pak Yus. You please to respond for the question. After that, we continue with other speaker to respond. Pak Yus. Pak Yus?
Yes, I'm here.
So if Pak Yus still cannot join with us,
hello.
Pak Rahmat, would you please to respond the question from the audience? Pak Rahmat? Yes, please, Pak Rahmat.
Thank you, Chairman. Some question comes up in the chat room. Then actually, some of them is may relate to my presentation. So actually, the South Pacific Convergence Zone, this is the low-level convergence between northeasterly wind, and it's also cooler and southeasterly winds, the higher latitude. So this is make a rain band and high pressure system that influence the Australia and another surrounding area. So increasing the convergence makes the rain band and cloudiness there. So this is one of the main source of the precipitation. And also the variation of the wind stress convergence that associated with this phenomena also can affect cloudiness and convection. So this is can increase the rate of precipitation. Then in terms of the oceanic surface, the variation of the wind stress curve, which is like a Ekman pumping, associated with the SPCZ can also influence the ocean circulation, then upper ocean salinity stratification. This is also can be a source of the convergence zone over the area. So this is kind of similar for the some question comes that the SPCZ and the double ITCZ. This is actually the aspect South Pacific Convergence Zones is the portion of the ITCZ. Sometimes we call the northern part of the ITCZ and southern part of the ITCZ. This is actually the similar, which is timely is the seasonal variability. There is also affect the similar influence with the intertropical convergence zone. I think this is my comment, and also one thing is the South Pacific Convergence Zone and IOD, I think timely is the different. I mean, time variability, SPCZ is actually the mostly dominated by annual variability or seasonal variability, and the IOD is the interannual variability. And this our presentation is a construct for indices according to the strength of SPCZ and also area of SPCZ. But in this presentation, still look at how the strength of SPCZ can affect rainfall over Indonesia. I think that's my comment. Thank you.
Okay, thank you, Pak Rahmat. So we back to the Pak Yus. Do you have already can join with us?
Yes, if you could hear me.
Yes, Pak, please.
Yes, I hope you can follow me now. Yeah, I really am sorry that I missed the question, but I already answered the question that was sent by Miss Dian later after my presentation. So could you read the question for me again, please? Because my computer, I mean, my Zoom was restarted several times.
Yeah, maybe Miss Dian asked about how from the government or something, how to implement the early warning system for the floods and for the landslide or something else.
Yes. Thank you, Pak Erwin. Actually, I already read this before and already give a little clue. This thing actually was not in my presentation and was not in my study past years, but it will be in my study this year. That we will investigate more on social intervention. This thing is important because after then we will know how to disseminate an early warning system, because we need to understand how people in Simalu, for example, I'm speaking about early warning system in general, but the successful one was in Simalu. How the early warning system was disseminated from generation to generation, and then apparently when disaster strikes, people already understand the system and then can respond accordingly. And this should happen, I suppose, not only on tsunami, but also on other disaster, even though on flood or on landslide. I think we need to learn from the community on how they respond naturally, and then we disseminate or interfere the other society, the other community with the idea. Thank you, Pak Erwin.
Okay, thank you, Pak Yus. So I think the same, or maybe I think the similar question may be almost the same with the Paul, because how to disseminate the information is very important for us as the mandatory of the agency. So I think maybe in the future, maybe we need to how to make some more efficient for the dissemination, and then make the people understand what the meaning of the information. So for next question, maybe I ask Pak Urip. So Pak Urip, you have some question from Pak Wendy from Lapan. They ask about how to access the data and how to get the data freely. I think maybe it's a very curious question from the users. Pak Urip, please.
Okay, thank you, Pak Erwin. Thank you, Pak Wendy. This is the classical question when BMKG present about the data. So the access data is very complex. Yeah. Okay. In principle, the data is provided freely, free of charge for non-commercial purposes. But it must be follow the data access regulations. For example, we have some regulation. The data is categorized into 3 levels. Level 1 is raw data, and then level 2 derived data, and level 3 is information. As your question, the high temporal rainfall data is categorized as level 1. So to get this data, you have to through cooperation. For example, joint research with BMKG, or you can request for non-commercial activities by submitting the proposal. For example, for the student from the university can submit the proposal of the research. So, and then we can discuss what the objective and what the need of data, how many data. But as your question to assess the whole Indonesian data, so I think it need to discuss why you need all the Indonesian data, all over Indonesia. So I think if you want to get all access data, you need to submit proposal, especially for the data level 1. Okay, thank you, Pak.
Okay, thank you, Pak Urip. Maybe I ask Pak Wendy if you have some more question. Maybe you can contact Pak Urip directly how to discuss and then how to get some specific data for this purpose.
Yeah,
so again, thank you, Pak Urip. And then now I invite Mr. Adrian Matthew. There are some questions for you. And then maybe you already answered in the chat room. Maybe if you want to respond directly, you please.
Yeah. So I've answered some of the questions in the chat room. I've seen that there's one that I hadn't answered, which was asking why are some of the vorticity source terms so much stronger in one hemisphere than the other? For example, the zonal and meridional advection of vorticity are very strong in one hemisphere but weak in the other. So to answer that, I've done some other work that I didn't have time to show, where I've split the advection of vorticity into its components. So I've split it into the part due to the basic state and the part due to the CCKW, the wave perturbation. And I think this difference in the hemispheres is due to the impact of the basic state. So you can get advection of the CCKW vorticity by the background winds, and those background winds are different in the different hemispheres. So that leads to quite different source terms in the two hemispheres. So that's a really interesting thing to follow up on, because those background winds will change with the season. So it's likely to be quite seasonally dependent, and it'll also change with the location. So I was just looking at what was happening over the Indian Ocean here, but as we move to different locations around the equator, I would imagine that those background advections are going to be rather different, and we might get rather different propagation characteristics when we do that.
Okay. Thank you, Adrian, for your answer. So for the next question, maybe I need response from Dr. Gard. Maybe Dr. already leaving the meeting. So for the next, Paul, do you have some response for the question?
Yes, I do. Thank you.
You have some question from Bu Nelly and then other participant.
I do. The aviation is a very good question. An illustration of that at our major airport here in the UK called Heathrow Airport. We used to produce all our TAFs, our aviation forecast products, from Heathrow Airport. We no longer do that. That's now centralized in Exeter. But we have introduced our meteorologists back at Heathrow Airport, and they are equipped to provide advice. They don't produce anything, they talk to the client and the customers at the airport, and they work with their systems, they work with their technology and the people to better manage the Heathrow Airport. So it's a very different skill, different role that our operational meteorologists are performing at Heathrow Airport than they did even 5 years ago. So that's based on impact. So impact-based forecasting and warnings is as much as training, skilling, and equipping our people to deal and work with other people to manage the impacts of weather, in this case on aviation at Heathrow Airport. That's a good question. Hello, Nelly. The other question about the challenges, oh my goodness, where do you start? I think the first one is social science. I think there's still a lot to understand people's reaction to warnings and what they do. I think there's still a lot to learn, and we've seen that in many examples. Haiyan was a good example in Vietnam when they were warned of Haiyan and they understood it to be a wind warning because it's a typhoon, not a rain. And therefore they protected themselves against wind, which meant they buried everything in the ground, which was vulnerable to wind. But unfortunately, it wasn't the wind that was the damage, it was the flood. So that lends to the hazards that come together, compound hazards, and how they linked and how we manage that and warn against that. We often find it's not just one hazard on its own, it's lots of other hazards that happen at the same time. So consolidating that, communicating that, having a clear understanding of what people do when they receive those type of warnings, I think that's a huge challenge. And that's something we need to work together as a partnership going forward. So hopefully that answers the two questions, one about aviation and the other one about the challenges of impact-based warnings.
Yeah, so Paul, this is my, from my view from for you. So is there any comment if the user asks you about the action, what to do after they get some warning? So the order of the evacuation or something, so it is come from the Met Office or come from the other agency, how to manage the warning?
It's a good question.
Ask about the what the action of the user, how to. So because from the BMKG we don't have some mandatory to make some recommendation for the action. We only deliver the information for the public, not until the action, how to recommendation.
So I created a natural hazards partnership in the UK with the Cabinet Office on the realization that it's best if all the voices of all the agencies are unified. So it's not just the Met Office who has a voice, but also my flood agencies, the civil protection authorities, the police, the fire brigade, they all have the same voice. And we have found in the UK that reaches far more impact than one voice alone. And so building a natural hazards partnership with all the agencies and government to manage when we have a big impactful event is the way we feel we can reach and reduce the impact on people. And that's why the last image I had with Nelly and the CIFDP in Indonesia is such a fantastic example of that working in action. Partnerships working together to manage the impacts of climate-induced hazards.
Okay, thank you very much for your response. I think we have the same experience for that. So for the last response, may I ask Bu Erma? So would you please to respond some question from the floor? You still mute your microphone.
Okay, thank you about the question. So the first question is about the verification issues of Sadewa operationally. Yeah, the second one is about the sample of precipitation, extreme precipitation in my research. I want to answer the second question first, okay? for the extreme precipitation sample, in our research, I make 50. I make the first one. The first step is I make filtering of the rainfall data. So I just considering significant rainfall. Okay, this is the first step. You should know about it. And the EMP have 50 sample of significant rainfall, which is the precipitation is correlated statistically with the extreme precipitation event. And I already identify with the floods of Jakarta. So there are many big floods, several floods in Jakarta, and that years of the flood is EMP event. So it's perhaps answer your question about the how many the precipitation event I use in my study. This is the first one, and the second one is about the verification issue of the Sadewa. You know, in Lapan we operationally 10 years Sadewa, and this is the very good question about the how the verify our NWP, which is operationally 10 years during 10 years verification. Several research about that. So many methods apply. We following Palmer, of course, in ROC diagram, yes and no, alarm, false and true alarm, and such method we apply in our research. Also, we try to innovate the radar precipitation. Okay, the radar precipitation, we deploy many radar because this is very cheap. We modify our radar, our ship radar to identify the signal of precipitation, rainfall data. So we deploy many radar. We call it Santanu, and we have still 10 years on-site location for Santanu, and we try to more, maybe 1,000 radar deploy over Indonesia to cover and make a better understanding about very difficult on-site because the topography and complexity of the ocean, land sea composition and others issue about that. So we need to make many radar for deploy the verification first about the instrumentation. And of course, in collaboration with BMKG, I think you can answer Pa Erwin, because he is a leader for the project of precipitation of predict of precipitation from Sadewa, and from Lapan is Pak Ibnu. We have strong collaboration with development and research in BMKG for this project in verification of Sadewa. This is very I think big challenge, big project, and we need still more. We need still more data, many data from BMKG, I think, because BMKG have so many station, ground-based station. So the issue, the current issue is how we can accessible the data from BMKG freely and aggressive like European, like Copernicus is very aggressive to make database freely to access in all world to save the world. I think it's very interesting to make framework or understand about the freely of data, because this is our network, our strength of nationality of Indonesia, I think. Thank you.
Okay, thank you, Bu Erma, and then thank you for all the speakers. So I regret that we have to conclude and finish our session now, because we still have other session for the records room. So again, thanks for all the speakers. I think all the discussion and all the presentation very interesting and very useful for us. And then maybe if someone still interested with the topics, maybe they will contact directly for the presenter. So again, thank you for everyone. So I say thank for all of you. We hope we can meet again and then other meeting. So I back to the Bu Sela. Thank you, Bu Sela.
Okay, thank you to Dr. Erwin for leading our wonderful discussion this afternoon. And once again, thank you to all speakers. So we learned so much from your talks. So here we come to the photo session. Please kindly activate your camera so that we could capture your beautiful smile in this occasion. So please be prepared for the slide 1. Give us your best smile. Okay. Okay, thank you. Next for the slide 2. Cheers. And the slide 3. Slide 4. And the last slide. Okay, thank you so much. So this is the end of the plenary session. Please kindly stay on your seat because next we will proceed to the parallel session. I would like to recall that this conference has 5 parallel rooms, namely Basic Science in room 1, Modeling in room 2 and 3, Observation in room 4, and Services in room 5. Participants are expected to join the room according to your interests. To enter the room, you may click on the breakout room menu that is provided on your Zoom screen and select your room preference. And again, I would also like to encourage participants to visit poster presentation room in the ICTMAS website, and please leave comment and question regarding to the poster. Once again, thank you all for joining us, and I hope you have a fruitful discussion ahead. So I'll see you tomorrow. Wassalamualaikum warahmatullahi wabarakatuh.
Indonesia merupakan negara kepulauan yang berada di garis khatulistiwa, terletak di antara 3 lempeng aktif, 2 benua, dan 2 samudra, sehingga menjadikan Indonesia sebagai negara maritim dan agraris. Tidak hanya memberi keindahan, Indonesia kaya akan sumber daya alam yang memberi kesejahteraan kepada masyarakat luas. Namun di balik keindahan itu tersimpan potensi bencana. Kondisi alam itulah yang menjadikan peran BMKG sangat penting. Penduduk yang padat, pembangunan infrastruktur, perkembangan industri, dan tingginya penggunaan alat transportasi sangat berkontribusi terhadap cuaca, iklim, dan kualitas udara. BMKG merupakan lembaga resmi yang menangani masalah cuaca, iklim, kualitas udara, gempa bumi, dan tsunami. Sehingga BMKG sangat erat kaitannya dengan keseharian kehidupan masyarakat di Indonesia. Dari aktivitas pribadi Dr. Onen di Bogor, sejarah pengamatan meteorologi dan geofisika Indonesia bermula. Puluhan tahun berganti, sekian banyak perubahan terjadi. Setelah penyerahan kedaulatan RI 1947, Lembaga Penelitian Cuaca dan Iklim diberi nama Jawatan Meteorologi dan Geofisika. Barulah melalui Peraturan Presiden Nomor 61 Tahun 2008, namanya berubah menjadi Badan Meteorologi, Klimatologi, dan Geofisika atau BMKG. Dengan SDM yang handal dan profesional, kami senantiasa memberikan informasi yang cepat dan akurat. Untuk lebih mendekatkan diri kepada masyarakat, BMKG meluncurkan aplikasi dengan nama Info BMKG yang memberikan informasi terkait cuaca, iklim, kualitas udara, dan gempa bumi. BMKG memiliki 186 unit pelaksana teknis pengamatan yang tersebar di seluruh Nusantara. Kami senantiasa memberikan informasi cuaca untuk penerbangan, maritim, dan pariwisata. Informasi iklim untuk pertanian dan ketahanan pangan. Informasi kualitas udara untuk mengantisipasi perubahan iklim. Informasi gempa bumi dan tsunami. Serta informasi terkait hilal dan penanda perubahan waktu. BMKG senantiasa menyajikan informasi secara rutin terkait cuaca, iklim, kualitas udara, gempa bumi, dan tsunami. BMKG memiliki stasiun pengamatan meteorologi, klimatologi, geofisika, dan Global Atmosphere Watch yang tersebar di seluruh Nusantara. BMKG memiliki 120 stasiun meteorologi yang berguna untuk mendukung kelancaran transportasi udara, laut, dan darat. Setiap harinya stasiun meteorologi mengambil data secara manual dari taman alat dan radar cuaca. Data tersebut lalu diolah sehingga menghasilkan produk layanan informasi prediksi cuaca yang bermanfaat untuk kelancaran transportasi, pertambangan, pariwisata, olahraga, dan kesehatan. BMKG memiliki 27 stasiun klimatologi. Setiap harinya stasiun klimatologi mengambil data dari taman alat. Data tersebut lalu diolah untuk menjadi dasar prediksi cuaca dalam jangka waktu tertentu. Prediksi cuaca yang kita baca setiap hari adalah salah satu produk dari pelayanan stasiun klimatologi. BMKG memiliki 31 stasiun geofisika. Setiap harinya stasiun geofisika mengambil data dari taman alat dan diolah sehingga menghasilkan sistem peringatan dini gempa bumi dan sistem peringatan dini tsunami. BMKG memiliki 3 stasiun pemantau atmosfer atau Global Atmosphere Watch. Stasiun GAW terletak di Bukit Kota Tabang, Sumatera Barat, Bariri, Sulawesi Tengah, dan Sorong, Papua Barat. Global Atmosphere Watch bertujuan untuk mengawasi efek emisi gas rumah kaca dan parameter yang berada di atmosfer bumi. Kami telah menjadi Center of Excellence di kawasan regional untuk program pendidikan Taruna MKG. Sekolah Tinggi Meteorologi, Klimatologi, dan Geofisika atau STMKG adalah sekolah tinggi kedinasan di bawah BMKG. Nantinya, lulusan STMKG akan diangkat menjadi aparatur sipil negara BMKG dan bekerja di kantor BMKG di seluruh Indonesia. BMKG pun secara berkala menggelar sekolah lapang iklim pertanian, sekolah lapang gempa bumi, serta sekolah lapang iklim nelayan sebagai bagian dari komitmen untuk mengembangkan pelayanan informasi cuaca dan iklim maritim. Kami terus berinovasi dalam menyampaikan informasi demi kemajuan negeri, menciptakan masyarakat yang lebih peduli, mencegah terjadinya bencana alam seperti banjir, gempa bumi, serta tsunami. Mari kita wujudkan Indonesia yang lebih mandiri. Bersama BMKG, senantiasa memberikan informasi yang cepat, tepat, akurat, luas jangkauannya, dan mudah dipahami.
School of Meteorology, Climatology, and Geophysics is a professional official education institution in the field of meteorology, climatology, geophysics, and instrumentation, under sponsored program of Meteorological, Climatological, and Geophysical Agency. School of Meteorology, Climatology, and Geophysics trains senior high school graduates to become high-detected analysts to improve the quality of services in meteorology, climatology, and geophysics. Academy of Meteorology and Geophysics, or AMG, was established in 1955 at Bandung Institute of Technology, or ITB, which then moved to Jakarta 1960. AMG became Education and Training Center for Meteorology and Geophysics in 1978 under organizational structure of Education and Training Agency in Ministry of Transportation. Later on, in 2000, Training Center for Meteorology and Geophysics renamed again as Academy of Meteorology and Geophysics, and its campus moved to Perhubungan 1 Street of Pondok Betung, Bintaro, South Tangerang. In 2004, AMG was under organizational structure of Meteorological and Geophysical Agency, or BMK, as a governmental agency. In 2008, BMK became Meteorological, Climatological, and Geophysical Agency, or BMKG. But the organization and management of AMG remained unchanged. In 2014, AMG officially became STMKG, or School of Meteorology, Climatology, and Geophysics. STMKG held higher education in meteorology, climatology, geophysics, and instrumentation for 4 years, equivalent to undergraduate program.
Success is determined by the quality of human resources. STMKG has the vision and mission of contributing to build human resources in a sustainable manner. The vision of School of Meteorology, Climatology, and Geophysics is to create the cadets who have the reliable, competitive, and absolute education and training human resources in the fields of meteorology, climatology, geophysics, and instrumentation. Mission of School of Meteorology, Climatology, and Geophysics are: first, preparing cadets to become member society of meteorology and geophysics who have professional skills in the fields meteorology, climatology, geophysics, and instrumentation. Second, spread knowledge in the field of meteorology, climatology, geophysics, and instrumentation, seeking to improve the implementation of public welfare and enrich the national culture. The third, carry out research that aims to develop the application of science in the field of meteorology, climatology, geophysics, and instrumentation.
Provide 4 departments that are Department of Meteorology, Department of Climatology, Department of Geophysics, and Department of Instrumentation. Education is organized within 8 semesters or 4 years. is a branch of science that studies the atmosphere and its phenomena. Cadets majoring in meteorology are demanded to be able to conduct the analysis, data processing, and providing services in the field of aeronautical meteorology, maritime meteorology, and meteorology for public services. Climatology is a branch of science that studies long-term weather conditions, or often called climate. Cadets majoring in climatology demanded to be able to conduct the analysis, data processing, and providing services in the field of climatology and air quality, and also become a reliable expert climatologist, which has global conception. Geophysics is a branch of science that studies about the physical process that occur on Earth. Department of Geophysics